All right, so I've been getting a lot of questions about the curve, understandably. So I hope my Canvas announcement last night helped, but just to kind of go over that a little bit more, the way I'm going to curve the class is once final grades are in, I'm going to calculate your raw scores based on exactly what I said in the syllabus. So without a quiz drop, it'd be 45% quizzes, 5% FNTs, 50% final. And if I'll calculate your grade with a quiz drop, so meaning I'll drop a quiz and raise your final weight with that corresponding percentage of the quiz, and just give you whichever of the two is higher, right? So if you do better on your final than you did on your lowest quiz, then it will just kind of replace that grade is another way to think about it. But anyway, I'll give you that quiz drop if it helps you. So if you missed a quiz, it definitely will. And then calculate then that'll be like the distribution of raw scores for the class. This is all before DL grades. So then I will implement the curve. And the way I curve it, instead of changing your raw score, I'll just decide what the cutoffs for each grade are. So like what's an A, what's a B, A plus, B minus, whatever. And I'll make those based on the percentages that I have to give. So the department mandates this because the school does. I don't know, but I can't just give everyone A's or everyone C's, whatever. They demand some distribution, and it ends up being mostly B's and C's with a bunch of A's, and I think some D's. The way they write it, I think like there have to be a couple D's, but there's no like minimum amount of D's and F's or something like that. I don't know, but there's a distribution I have to follow, and so I try to make my cutoffs such that it maximizes that. So give the maximum amount of A's and B's and C's I can, minimizing the amount of D's and F's. Generally, you don't fail unless you like missed too many DLs or something like that. It's possible if you're but yeah, generally it's not. So that's the way I'll make the cutoffs. Again, trying to maximize the amount, and it usually works out to be that the average is about a B minus. So that's kind of where it gets weird, like given the cutoffs, what like the average means. But one way to interpret that is given that the quiz average right now is about a 6, it's a little above a 6, but right about a 6 out of 10, if you have a quiz average that is a 6 out of 10, then that should work out to about a B minus or an 80. I say B minus / C plus because depending on like the exact numbers of grades and like outliers, which I can't predict, it could be like 79 point something or 80 point something, but it's right about an 80. So if you have an average quiz grade, that should be about an 80. Then your DL grades apply, like after the curve. So yeah, a high pass is 3 points on your average, in your final average post-curve, and a mid-pass is 1 point. On Canvas, I'll make an announcement about this, but on Canvas, for the DL grade column, you will see, most people will see a 0 out of 3. That doesn't mean you're missing any points. That's just because like high pass, mid-pass are extra credit. So you're not failing anything or losing if you got a pass. Yeah. So what is the 3 points? Like 3% added to your grade? It's 3. Yeah. So it's 3% added to your grade. So let's say you got a 65, and a 65 works out to be a B minus. A 66 works out to be a B minus. Your 65 would be a C plus, but then if your DL grade is a high pass and you get 3 points added to it, that brings you up to a 68. Now you have your B minus or maybe a. So yeah, I mean, basically the idea is that a high pass should increase your GPA. Essentially, it should bring you from a B minus to a B or a B to a B plus, whatever. And a mid pass is, well, it's a point on your average, so it helps, but. And your TA determines that, right? Yeah, so your TAs are going to determine that based on, it's not about your grade, it's not about how many questions you got right, it's just about participation. So if you were present and effortful and helping others and trying, just an important part of your DL, yeah. How many high passes are given out and how many mid passes? Right, so the way we're doing it is for each class, so that's not like but for each DL of all the A and B people, which is 30 to 35 people, TAs have 12 points to give out of high passes and mid passes. High passes being 3, mid passes being 1. So that's either 3 of each or 3 high passes. Yeah, so 3 of each, 2 high passes, 6 mid passes, something like that. The only stipulation is they have to give 1 of each. So it can't be 12 mid passes. It can't be 4 high passes. You find that out after the final. So the idea is that it should not have anything to do with how you're doing in the course. I know it's tempting to give people that need it the most the high passes and stuff like that, but at the end of the day, the purpose of it has nothing to do with your performance, like quantitatively. It's just showing up and putting in effort and interacting with your peers. So, yeah, there should be no opportunity. Like once the DL grades are put in, then you'll get your final grade. Like you can't like reach back out and ask to change it or whatever, because that just changes what they're all about. But you will see them along with your final grade. And once the finals are graded and I calculate your final grades, we don't have a ton of time because our final's on a Friday night, and then the grades are due on Wednesday, I think, the next Wednesday. And of course, we need time to grade your final. So I think on Wednesday, essentially, I'll release your final grades, like your letter grades for the course, and then you'll have however many hours, but really only that day, to take a look and submit a regrade request for mistakes that were made in like my calculation, essentially. I know it's not a lot of time, but it's just like what we're forced to at the time of our final. It's not like the end of the world if you didn't get something in and like we really, really made a mistake, then there's grade change forms and whatever, so you're not like screwed forever. It's just like, it's really important that we get this done quickly. But anyway, yeah, so your final grades you'll probably get on the Wednesday following the final with your letter grades and your final that you can look at in GradeScope and submit regrade requests, everything like that. Any other questions on grading schemes? So yeah, anything's about like, I would prefer my quiz average to be a little bit higher. I mean, at the very least, just because like confidence, like I know when I get a 60, even if I'm told that's above average, it still doesn't feel great. So like I know that's an important thing. But at the end of the day, we do have a wide grade distribution, which is helpful because when I curve, it's much easier to take a wide distribution and like narrow it and move it up than it is to take a distribution that's like pointy and right between like 8 out of 10 and 10 out of 10 and have to spread it out. Like I'd much rather make the cutoff for a B very low than make the cutoff for an A very high, right? So that's just my kind of philosophy. And it's worked so far, so I think it'll work. Any logistics stuff? All right, so today I'm going to kind of review kinematics and do a bunch of examples with that. That's the stuff you've been doing in DL with graphing position, velocity, and acceleration, and working back and forth between forces. And we'll also connect it a little bit with momentum and that side of stuff that we've done before. So Newton's laws I just put up here. I'm not going to spend a lot of time with them, but first and second law are pretty much the same thing. It's just saying that your change in velocity or your acceleration is due via your mass to the net force, right? The direction of the net force is the same as your change in your velocity, and if there is no net force, then you won't have a change in your velocity. Doesn't mean your velocity is 0, but it's not changing. The third law, we also kind of found this with momentum charts, but any force on an object has an equal and opposite force on the one that caused it. So anytime we draw a force that doesn't look like it has a third law pair like this, for instance, gravity, most or many of our problems involve a ton of forces from gravity, and we never, I don't think we ever, account for the force on the Earth by us, which also does exist. So it's not like this third law is like selectively involved. It's always true, but we only usually apply it to objects within our system, right? We never include the Earth in the system. We don't care about the immeasurably small, tiny change in the Earth's speed, which like technically there is. Like every time I drop something, the Earth comes a little bit closer to that object I dropped. But it's impossible to measure, and so we just don't care about it. But the third law always applies. So what is acceleration? Well, we know it's a change in velocity over a change in time. On this slide, it's written as dv dt. That you can just read that as the delta that we normally see. D is what we use in calculus. It just means that the change is infinitesimally small. So instead of over our delta t being like a second or two, it's just as small as possible, an infinitesimal change. But it doesn't really matter. For us, it's the same as delta. So this is a vector equation, and we can split it into all its components, so x, y, and z if we wanted to, but those all function independently. So just like before, like the whole quarter, we can take a magnitude and direction, split it into components, and combine them back at the end, and they work completely independently. Acceleration, though, it's very important to remember, is tied to the change in velocity. So the thing that tells us what an object is doing, its motion at an individual moment, is its velocity, not its change. I can have any combination of velocity and change in velocity. In other words, if I tell you what my velocity is without any other information, you have no idea what its change is. Like you have no idea what the delta v is over delta t. Similarly, if I tell you only what my change in velocity is or only what my acceleration is, you have no information about the velocity itself. And so I think it's really important, because this is a mistake we often make, is like hearing an acceleration and then automatically like imagining some resulting motion, that the acceleration itself doesn't tell you what the object is doing at that moment. It just tells you how it's going to change moving forward, or how it has changed. So yeah, acceleration can be in any direction, and a particle at rest can be accelerating. Those two things are kind of related to what I just said. That an object, we know if it's like moving one way and the acceleration is opposite it, it will slow down, stop, and then turn around. That whole time its acceleration was constant, but it had a positive velocity, zero velocity, negative velocity. So the acceleration clearly does not tell us about the velocity without more information. And then finally, even if a particle is accelerating, its speed may or may not be changing. So that's like the case of circular motion. When we have like a ball swinging around with a rope, we know there's this constant force on it that's changing its velocity. That's why it goes in a circle, but it's changing the direction, not the magnitude or the speed. So it's changing, another way to think of it, the components, right? It's exchanging y for x. So the acceleration, we could still plot it out, and we would see, like in the y direction only, the velocity is changing. But we have a change in the x such that when you combine them together with the Pythagorean theorem, you'll get the same magnitude. So long story short, acceleration needs to be looked at kind of from a distance, and don't be too quick to jump from acceleration to resulting motion. And just a note for the problem solving, we are focusing now on like kinematics and forces and accelerations, but all of this is the same, really the same physics as the energy and momentum way that we worked on so much the rest of the quarter. And I showed that when we turned delta p equals f net delta t, when I just expanded this and moved it around and turned that into f equals ma, it's showing it's the same physics. It's just the two different ways of looking at things have complementary but different strengths, I would say, in understanding problems. And so later in the lecture, we'll do something that shows both. Okay, so here's an example. I won't spend too long on it, but it's a lot on this slide. We just want to look at the kinematics of an object that is falling with gravity, under the influence of gravity and nothing else. And we'll say it has some initial downward velocity. So some initial Vy naught that's negative, and the only force that's acting on it is gravity, and so its acceleration is negative g in the y direction. Right? So that's our given. We'll also say that maybe it starts at a height of 0. If we look at the graph, it looks like it's at 0, but that's not super important. Anyway, we want to figure out how long it takes to hit the ground, and maybe what its speed is when it hits the ground. Basically figure out everything about this object falling and make the plots. Well, they're already out here, but we'll walk through them together. Okay, so I think it's easiest to start with velocity. So the kinematics equation for velocity, well, I guess acceleration is even easier. We already kind of said it. AY is negative g, just meaning the only acceleration is that due to gravity, and this object is speeding up downward because gravity's pulling on it. And so my acceleration versus time graph is just this constant negative 10 meters per second value. That's it. And this is, I mean, you might have multiple sections of it, but you're only going to be responsible for problems where the acceleration is flat, like this. Maybe multiple different values, flat here and then there and there, but you're never going to have to do like a curved acceleration. So anyway, there's our acceleration velocity. Our kinematics equation for velocity is that our final velocity is equal to our initial velocity plus our acceleration times time. So to read this intuitively, our final velocity is certainly dependent on whatever we started with, right? So I just take my starting point. And then over time, that changes depending on what my acceleration is. And what is my acceleration but the change in velocity over time? So if we plug in our negative 10 meters per second squared, let's take a look at the units. The units of acceleration are meters per second squared, or really meters per second. That comes from delta v over delta t. So you can think of this term, this a times t, as meters per second. So like how many meters per second is this object changing? So like how much is its velocity changing each second? And so that's why we multiply it by t. This is the amount the velocity changes each unit time, and then we multiply it by the amount of time that elapsed, and that tells us how much it changed in total. So if my acceleration is negative 10 meters per second squared due to gravity, after 1 second, my velocity will have changed 10 meters per second. Right? After 2, it'll have changed 20 meters per second. And so my final velocity is just going to be whatever my initial was, minus either 10 after 1 second or minus 20 after 2, so on and so forth. And so if we plot that out, this is just the equation of a straight line, y equals mx plus b. And so our b, our y-intercept, is just whatever our initial velocity was, right? At time t equals 0, we have that negative initial velocity, this vy naught. And after that, our slope is negative 10. So we just get this downward trending line, which shows an object that's moving down and continues to move down at a faster and faster rate. We don't know anything about why it's moving initially at speed vy naught downward, and it doesn't really matter. Whether we threw it downward or it was already falling and had sped up this much and now continues to is irrelevant. All we know is that this is the velocity it has at our starting point, and this is the force that's on it. So a lot of times if I had written a problem like I'm throwing a ball downward, a lot of people will think to write, well, of course, the force due to gravity, but then also add a force due to my throw, which certainly does exist while I'm throwing it. But here we're not concerned about that point. We're concerned about after the ball is in the air and falling, once it's left the hand. And once it's left the hand can't apply any more force on the ball. It's given it whatever velocity it wants. It's given it this vy naught, and now it's starting. And now the only change can be due to the force that's still on it, which is gravity. So whenever you have like some sort of collision or something thrown or coming out of a cannon, whatever, it's important to recognize that initial force is probably not part of the time interval that you're concerned about. It was just like the impetus to give it an initial velocity. Okay, so anyway, we have our velocity graph. Now let's turn it into position. First, the equation for it, this kinematics equation, our y final equals this big mess. But this big mess can be relatively intuitively read too. Our final position is equal to, well, of course, our initial, depends on where we started, plus some velocity times time, right? Velocity, that's our change in the position due to whatever our initial velocity was, right? So that's simple enough. But then we have this added term, 1/2 at squared, and the 1/2 and the t squared just come from calculus, but we don't really care about that. What we care about is that this term is just accounting for the fact that we don't have a constant velocity. So that's after time t equals 0, our velocity isn't vy naught anymore. It's vy naught times whatever, or plus whatever change occurred due to the acceleration. And so this term accounts for the fact that our velocity is changing according to AY. So these three terms are still, again, I think intuitive. The first one, where I started. Second one is change due to how fast I was moving to begin with. And then the third part accounts for the change in the velocity itself. So if you plot this equation, no matter what you plug in for y naught, vy naught, and ay, this is the equation of a parabola. Right? It's like ax squared plus bx plus c, where time is the independent variable, and y is the dependent variable here. So you're going to get a parabola, but as you've probably seen, that parabola can be facing up, facing down, really skinny, really wide, moved, like shifted all around, whatever. But it always is a parabola. And really what that means, a parabola is just something that has this one part that has a slope 0, and then it's curved in the other two directions, either up or down. So here if we plug in values relevant to this equation, here they plug in h for y naught, even though on this graph it sure looks like y naught is 0, but it doesn't really matter. This is some constant. Call h 0 for now. Vy naught is some negative number, and ay is negative 10 meters per second squared. And if we plot that, we get a parabola that starts at 0 and goes downward. At time t equals 0, we have some slight downward velocity. And then as time progresses, since our velocity, which tells us the slope of our position graph, is decreasing, that means the slope of my position graph is decreasing. And so it becomes, since it's negative, it becomes more and more negative. And so we get an object that's falling faster and faster and faster, which makes sense. So now to actually solve for some relevant quantities, if we wanted to know maybe how long does it take this object to reach the ground. So now maybe that's why they put h here. If we assume that the object started at a height of h, we want to solve for when its final height is 0. Right? Now we have no unknowns here, and we can just solve, or one unknown, sorry, we can solve for t. So you can either use your calculator or whatever. I won't have you solve the quadratic equation like this on the exam, but maybe just a simpler version of it, but it can be done. And so we can find how long it takes to fall a certain height. And then once we have that amount of time, we can plug that into our other kinematics equation. So this is our velocity versus time. And so we could plug that time in here, and that would give us the velocity of the ball when it hits the ground. Yeah? Yeah, exactly. So if we wanted to solve this, we would just have this, and we don't know what this is, and we don't know what this is, t or v final, and so we would need to do more work. But yeah, in the first one we do know it. Exactly, yeah. So no matter what, if you're going to solve the quadratic equation, you normally set it up as 0 equals ax squared plus bx plus c. The c term is always just going to be y naught minus y final, or your change in y. So yeah, you're right. It doesn't matter what I call 0 at all. Just the relationship. Okay. What if we added an x component to this? So what if, let's say I did throw the ball, instead of throwing it straight down, I threw it straight down and to one side. Nothing would change about all the work we just did, right? The x and the y components are completely separate. When the ball has left my hand, the only force on it in the y direction is gravity. And so all of this work applies just the same. Yeah. I also, this equation popped up here. This is another kinematics equation that you'll see. It's derived using the same physics we already know. It's just a convenient restructuring. And if you notice, this equation here is missing time, which is helpful because if you don't have the time, this one might be more convenient to use. But you don't necessarily need it. You could always solve the other ones and work it out. So here, if we wanted to find the velocity right before hitting the ground, I don't know y final. That's what I'm looking, vy final, that's what I'm looking for. I know Vy naught, I know A, I know Y final, I know Y0. So I could have just used this equation, but instead I think I did the more intuitive thing, which is solving this way. Anyway, just so you know why this is here when it pops up. It's kind of weird, but it's helpful. Anyway, back to the thing. Now it has an x and a y component. Y components don't change because just the fact that it has some constant velocity in the x direction doesn't tell us anything about the y. And if we wanted to make these same plots for the x direction, it'd be really easy because our acceleration is 0 because there's no force in the x direction. Our velocity is constant, just whatever initial x velocity I gave it. And so my position is just constantly changing with a constant slope. And we can see what the position graph would look like if now we plug into our kinematics equation. A is 0, and so it just turns into the equation of a line. This x equals x naught plus vx0 times t. That's just like a y equals mx plus b style equation that looks just like the diagonal increasing line we plotted here, which just says the ball will continue at a constant speed for as long as it can. And so if we wanted to see how far the ball goes in the amount of time it takes to hit the ground, now we can plug in the t that we found on the previous slide in the y direction. That told us how long it takes to fall. And so if we plug that falling time in to our x translation equation, we'll get how far it went in that amount of time. And of course, the final velocity is still what it started with because there's no acceleration in the x direction. But here I think it's just kind of cool that something kinematics lets us do is connect the x and the y components via the time piece of it. So we could still do, like, we could figure out angles and stuff and magnitudes, whatever we wanted. But it's also cool that even though the x and the y directions can be solved for independently, we can find an interesting thing in one, or like find an interesting moment, here the time that it takes to fall, and take that piece and use it. Like we found that from the y components and then use that to learn things in the x component. So time is, there's no tx and ty. Time is, of course, shared between all of these. Okay, so let's do another example. We have a classic case of a box getting pushed on the ground. So y direction, very boring. Normal force and gravity cancel out. It's not moving up at a constant velocity, not moving down, so everything in the y direction is 0. Great. Let's look at the x direction. So now if we define the x as positive to the right, we have this push. That's a force that's pushing it, no friction, pushing it to the left. So we have a force that is in the negative x direction. And so we don't know what the mass is, but if we have a negative force, we know we're going to have some negative acceleration. So constant force means constant negative acceleration. Does that tell me what the object is going to do? Well, it tells me how the velocity of it's going to change, but what I wanted to emphasize here is that because, like, just seeing this, I would think, like, oh, the box is moving to the left, right? But that's not necessarily true. We just know that its acceleration is to the left. If I wanted to turn this into a velocity versus time, right, how is the motion of this object going to change over time? All the acceleration tells me is the slope of that velocity versus time, right? And here it's some negative value, so some downward slope. And so I can have 3 different categories of situations. The initial velocity could be whatever, but in general, it could either be 0 to start with, initially at rest, which means we start at 0 and then have a downward slope. So start speeding up in the negative x direction, getting faster and faster and faster to the left. Or let's say it's initially moving to the right, in which case I have an initial positive velocity in the x direction, and then, again, same downward slope, so I slow down until I reach 0, and then start speeding up in the negative y direction. Or I start with initially moving left, in which case again, same slope, but now I'm starting moving left and only speeding up moving left. And so we can see that our velocity versus time, this is our general kinematics equation, right? Vx equals vx naught plus ax times t. Our ax is not changing, right? That's our negative acceleration to the left. But depending on what this vx is, this vx naught, that's my y-intercept on this velocity graph, I can get very different behavior, right? We know the first one here, initially at rest, means an object is at rest and then starts accelerating, moving faster and faster to the left. The one in the middle, initially moving to the right, is the most complex behavior, where here we have, even though it's getting slower, we have a positive velocity to the right that's decreasing, getting closer to 0, reaches 0, and then becomes negative and starts speeding up. So in this case, the object is moving to the right, the force causes it to slow down and then turn around and move to the left. And so this, I think, is a good place to note one general rule, and I normally shy away from general rules like this, but this one is true. When the velocity and acceleration have the same sign, then the object is speeding up. So if velocity is positive and acceleration is positive, acceleration positive meaning I'm adding to my velocity over time. If I add to a positive number, it gets bigger and bigger, further away from 0, which means it's speeding up. Same thing for negative acceleration and negative velocity. Negative acceleration means I'm subtracting away from velocity over time, and if my velocity is negative and I'm subtracting from it, then it gets more and more negative, again, further from 0, which means I'm speeding up. If the signs are opposite, then I'm slowing down. So if I have a positive acceleration and a negative velocity, that means I'm adding to my velocity over time, right? So if I add to a negative number, it will get smaller, like closer to 0. Same thing, if I have a positive velocity and a negative acceleration, I subtract away from it over time and bring it closer to 0. So yeah, when they have opposite signs, slowing down. When they have the same sign, speeding up. And the direction of motion of the object is, of course, just determined by the sign of the velocity. If velocity is positive, it is moving to the right. And if the velocity is negative, it is moving to the left, regardless of what the acceleration is at that moment. So again, here, acceleration is one value throughout all time in all three of these situations, but we have an object that is moving to the left, moving to the right at various different speeds, and even going through 0, so even stopped. So acceleration does not tell you what the instantaneous velocity of an object is. Now finally, let's make one last step and move to make position versus time graphs for this object. So the conundrum we ran into here, where we didn't know what the initial velocity of the object is, carries one step further to the position. And that really just comes from, again, like calculus. If you remember, when you integrate, you always get this, well, unless you have bounds, you usually get this like plus c term, right? There's always this like added constant, and if that means nothing to you, don't worry about it, but that's what this is. When I integrate this acceleration versus time graph, that tells me what the slope is, but not where to, or sorry, if I integrate where the velocity is anyway. So I run into the same thing where if I take my velocity versus time and try to turn that into an x versus time, I'm missing the x naught. I don't know what my starting position was based on the velocity, right? I could tell you any velocity and acceleration, and that still doesn't tell me the location. So I'm just going to assume that they all start at x equals 0. Right, so x equals 0 is the starting point at time equals 0 for all three of these. And now, if we take a look at the first one where it was initially at rest and then starts speeding up to the left, we start at rest, so my starting velocity or my starting slope is 0. And then over time, I'm moving to the left, so I become more and more negative position-wise. And the rate at which I do so, in other words, the slope, becomes steeper and steeper over time. This is not exponential, right? It's not going to get infinitely steep. Like, it's not going to be asymptotic like an exponential. But so sometimes when I sketch them, it looks like that. But it's just important to note that a quadratic is different than an exponential. They have a different shape. If we started moving to the right, then our position is increasing at first, right? We have a positive velocity, and so my x is increasing. But that slope, because the velocity is going back towards 0, the slope is decreasing until the velocity reaches 0, passes through 0, in which case the tangent here, the slope of my x versus time is 0, right? So this point, the apex of this parabola, occurs at the same time as the velocity crosses through 0, and then it gets more and more negative. So it turns around, crosses the position that it originally started at, and keeps heading backwards. And in the third case, where we had a starting velocity that was negative, we start with a negative slope and just even get faster and faster from there. So these are all kind of like sections taken from a parabola. And just depending on what my initial position and my initial velocity was, that tells us like the stretch of it and where I put it. But still, we're just working with either an upward parabola, a downward one, then we stretch it, and then we like locate it. It's the same kind of idea with exponentials for this course, where if you're really comfortable working with the algebra, great. But if you're not, you just need to kind of memorize the form almost. Not memorize, because I will give you these equations, but just learn what the key things that you need to know are, which are what's the intercept, like where does it cross the x-axis, where is its peak, so on and so forth. Yeah. So questions about this example? Now we'll transition into some clicker questions. All right. You're in an elevator, and you're standing on the first floor, and it's at rest to start off with. Then the elevator brings you up to the third floor and comes to a stop there. And so we want to graph our acceleration as a function of time. So we're stopped, go up to the third floor, and stop again. I'll give you 10 more seconds. Okay. So the answer is B. And let's see why. So, well, yeah, let's maybe go through these first and see why the other ones can't be true. So we know that we start at rest, and then in order to move upward, we're going to need a positive velocity at some point, right? So our delta v over delta t is going to have to be positive. In other words, our acceleration is going to have to be positive in order to get us moving. And so I need my acceleration to go upward to start with. After being at rest, we need it to go upward. All of these satisfy that, right? These all start with some increase in acceleration, okay? Then I need it to stop at some point, right? I need to come back to a rest at floor 3 when I get there. And so that tells me I need to go from having some positive velocity to 0, which is a negative delta v over delta t, right? That's a decrease in velocity over time, which means a negative acceleration, an acceleration that's less than 0. And so right away, that tells me A, B, and C, A, C, and D, none of these have any negative acceleration, right? They're above the x-axis or the t-axis the whole time. And so none of those are possible. They describe different scenarios, but all of these have my velocity going up and maybe staying constant for a while, and then going up again, but never coming back down. So these have no way of getting me to a stop. If we want to look at one in more detail, like C, kind of like I just said, we get this little burst of acceleration. So my velocity increases here. Then my acceleration is 0. So that's fine. I sped up, and now I'm moving at a constant velocity upward because I gained it here. But then when I get to floor 3, I gain some more. This is the positive acceleration. So I just get to floor 3 and then speed up and keep going, which is no good. And then A and D are kind of similar, where they just gain a lot of velocity and eventually stop gaining it. They eventually come back to a constant velocity, but never slow down. So B does have a negative acceleration, and let's see if this makes sense. We're at a rest, we have some burst of acceleration, and so we speed up, and then the acceleration goes away. So we have a positive velocity that's constant, that's us going up. And then we reach floor 3, and there's a negative acceleration that looks equal and opposite. So we get a burst of decrease in velocity, and then back to constant, which makes sense, right? We get a boost of velocity, hold it, hold it, hold it, and then get rid of it, come to a stop. And so B makes good sense for how an elevator might work. So now we can take a look at a more simplified version. So instead of, in reality, it would have those kind of curves like we saw before, because the way the machine works is probably not going to be perfectly on and off like that. But we can approximate it, and any problem that you would actually have to solve, we could just do it kind of piecewise like this, where acceleration is just a series of flat lines. It's just one value for a given period of time. And if if this question was asked on an exam, kind of conceptually, sketch the acceleration or something, it wouldn't matter whether you drew it like this or with the curves. That would be fine. I'm just trying to say that this is enough. Anyway, so we get the speeding up, then constant, and then slowing down. And so if we translate that into velocity, well, this velocity graph kind of gets rid of that constant time at the beginning. So for this first little section of the acceleration, we have no velocity and no change in velocity, so it should be 0. So whatever, let's put that to the left of the y-axis. Then we get this period of constant acceleration. So constant positive acceleration means we have a constant positive slope for v, and then my acceleration goes back to 0. So my slope goes to 0, but I have this constant positive velocity, and then I have a constant negative acceleration. So a constant negative slope, and then back to 0, so constant again. And so this does make sense. We have a velocity that's always positive, but it speeds up, then slows back down. We never go down, but we only go a finite amount up. And so if we did our position versus time, well, maybe I'll leave that up to you. But the position we know is always going to be increasing, because my velocity, which is delta y over delta t, right, is always positive. It's just positive at different amounts. Okay, questions on this one? Let's do another one. This one's a little more involved. So we have a ball that's rolling between two ramps, and it has an initial speed to the left. Right, so its initial velocity is to the left, and we're asking about the acceleration along the ramp. So don't worry about the x and y components, just how fast is it moving along the ramp, and how much is it accelerating in the plane of that ramp. If you get a way I recommend starting if you're stuck is, before you even think about the order of events, just for each section, when the ball is here, when the ball is there, when the ball is there, decide what direction your net force will be, which tells you what direction the acceleration will be. And then you can piece together how you want to put those together, what order will the ball hit this piece, and that piece. Then if you know the order and you know the acceleration at each point, you can assemble this. If that doesn't help you, then don't do that. But no, it can go up on either side. It's just the acceleration along the ramp, just meaning that when it's rolling up the left side, you don't have to break that down into like an x and a y. It's just whatever that acceleration is along that line. So yeah, assume the ball's going to stay in contact with the ramp, and it's not going to fly off the end. It's going to do what we expect. It rolls. You put a ball on a U-shaped ramp, it'll roll back and forth. I'll give you another minute or so. Okay, I'm going to stop us there. The answer is C, and let's see why. So we're going to follow the way of thinking about it that I described, where first we're going to say, what are the forces acting on the ball when it's at different points, and then we'll kind of put them together. Well, really it assumes the answer, but you'll see. So first let's take a look at when the ball is on the flat surface. So anytime it's rolling across the bottom, the forces acting on it are gravity and the normal force, and that's it, right? There's no force acting in the x direction. Just because it has some initial velocity in the x direction doesn't mean that it takes a force to maintain that. It just means that it's constant, right? So the ball rolls along to the left with no acceleration because it has no net force acting on it. And so whenever the ball is along the bottom, it will have zero acceleration. So that's going to happen for a little bit as the ball rolls to the left, but then it's going to reach the left ramp. And so while it's moving up the left ramp, now we have a net force along the ramp. We have gravity that points straight down and a normal force that points, well, perpendicular to the surface. So I won't go into super detail about breaking down the force, but we've done this enough times that we know the ball is not going to like sink through the ramp or float off into space, right? It's still going to have the normal force and one component of gravity cancel, so it stays in line with the plank. But then we'll have this excess force from gravity along the ramp that wants it to roll back down or wants it to slow down. But gravity is going to pull it back, which we all experience, right? If you put something on a hill, it wants to roll down, and that's because of this net force. So now our net force is in the positive direction, or like along the positive way of the ramp. So our acceleration has to be positive. It doesn't actually matter what the velocity of the ball is while it's on this left ramp, whether it's moving up it or down it or stopped. If this ball is on this ramp, the net force on it is to the right, and it's constant because gravity and normal force are not changing. So this is true while the ball is rolling up, coming to a stop, and rolling back. We're still at this same constant positive acceleration, right? So this interval here, we know like in reality what happens, the ball rolls up and down, and that whole time it's on this left ramp, but the acceleration is constant and in the positive direction here. Then the ball rolls back down, hits the bottom again, where we decide that there is no net force. So now it has a positive velocity, right? It goes up and rolls back down. Because of this positive acceleration, which turned its velocity from negative to 0 to positive, we have a constant positive velocity, which allows it to roll across, but during that time it has no acceleration and a constant velocity. Then it's going to hit the far right ramp, and we'll get a very similar occurrence, but flipped around, where now that excess component of gravity is pointing back in the negative direction, and so we'll have a constant negative acceleration. And that's true while the ball is rolling up the ramp, coming to a stop, and rolling back. Because again, this force setup, and thus the acceleration that results, have no dependence on the velocity. It just depends on the net force, which is due to gravity, and the normal force, which don't change. So we've devised our acceleration versus time graph here. Any questions on this? Okay, so yeah, we could extend this as much as we want. So we know that once it reaches the bottom of this ramp, it'll go back to 0, and then roll across, and then we're right back to where we started. So we'll get this repeating. Every time it hits the left, we get this positive, and every time it hits the right, it gets a negative.
One cycle is actually.
Yeah. So yeah, exactly. This is one cycle, but it would repeat indefinitely. In reality, there'd be some friction, right? And so they'd get slower and slower. But all right. So now, yeah. Because it says neglect friction. Yeah, if you're told that there is a velocity of it, that doesn't tell you anything about the neglect friction tells us that there's no net force. Okay. So now let's extend that same setup, but now draw me the velocity versus time along the ramp. So it will probably be helpful to take a look at the acceleration versus time. So do we all understand what the question is for a sec? If you don't have it copied down or something like that, or just to take another look, this is our acceleration versus time. So what should the velocity versus time look like? Let me say that again. When
the ball was going like up the ramp.
On the right or the left? Or it doesn't matter? No, the acceleration will be, while it's on that ramp, will be constant. Because again, the acceleration comes from the net force, and the net force is just due to gravity and the normal force, which don't change. So regardless of whether the ball is moving forward or backward, it doesn't really matter. The net force and thus the acceleration are constant while it's on that ramp.
So it's going so it's going up or down.
Same net force, yeah. So what the trick is, remember, if the velocity and acceleration are the same, one thing happens. And if they have the same sign, then one thing happens. But if they have opposite signs, then another thing happens.
And then when does it, so with this part of the graph, when it's negative acceleration,
Mm-hmm.
which part did that describe? Like, what was the velocity?
What do you, so what?
Is that when it's going like?
Exactly, yeah. So negative acceleration means that there's a net force to the left, which is when it would be on the right ramp that's angled that way. There would be that net force pushing it down.
So if it's negative, that doesn't mean it's like decreasing velocity. It's like increasing. It's like it's the opposite direction.
Right, yeah. When the acceleration just tells you how the velocity is changing, whether it's getting more positive or more negative. It doesn't tell you what the velocity is. So here, let's go over this one together. So the answer is A. Let's take a look at our acceleration versus time graph and try to work this out. So we start off with a negative velocity that's constant, right? So this, we know we start off with no acceleration, so no change in velocity, but our velocity is negative. So our graph needs to have a negative constant velocity to start off. A has that, B has that, C does not. C starts with a positive velocity, which is not, that would mean the ball starts moving to the right, which is not true. So C is out, but D has that and E has that as well. So far we've ruled out C. Now we know that that constant acceleration is, zero acceleration is followed by a positive constant acceleration, which means we are going to add to that negative velocity we just had. In other words, make it less negative by adding to this negative number. So A does that, right? We have this negative constant, and then we start to add to it, and the velocity grows toward the positive direction. B does not have that. Well, it does eventually, but B has this weird spike where it gets faster, right? The velocity becomes more negative, which there's nothing here that would have that happen, right? The ball is moving to the left, and then the ramp slows it down. There's nothing that would just cause it to speed up to the left. And so B's out. C's already out. D has this, right? We have a negative constant velocity, and then it starts becoming more and more positive, so that's good. And then E also has that. So now we're down to A, D, and E. So this interval, we know, has some interesting behavior going on during it. It is just a constant positive acceleration, but that's true for the whole time the ball is on the left side of the ramp, while it's going up to the left, and then when it's turning around and coming back to the right. It's still that constant positive acceleration. So we know our velocity during that time goes from being negative towards 0, so increasing towards 0, and then through 0 and positive, right? That would be the ball stopping and turning back around and rolling back to the other side. It needs a positive velocity then. So our period of increasing velocity, or positive acceleration, that comes from this first hump of the acceleration graph needs to climb through 0 and up to a positive velocity, where A has that, right? We start at our initial negative velocity and then have constant acceleration that slows us down and then speeds us back up in the other direction. D also has that, but E doesn't. E has this strange slowing down towards 0, so coming to a stop, but then speeding back up in the negative direction. That would be this ball rolling up the ramp, slowing down, coming to a stop, and then just starting to speed up again and keep rolling upwards to the left, which is not what happens. So now E's out. Now we're just between A and D. The other intervals we have this zero acceleration interval again, where it's on the flat part, where now it has a positive velocity that's not changing. Both A and D have that, right? They have this middle section where the velocity is positive and constant. That's the ball rolling to the right. And then finally, when it comes in contact with the right side, we have the opposite of what happened before, where now we have a constant negative acceleration. So we're going to subtract away from our velocity at a constant rate. So we'll have a diagonal line that slopes downward, and that's going to slow us down and then bring us in the other direction. And both of A and D show that, where the velocity decreases from a positive constant to 0 and then back the other way, and then once it hits the ground again, or the middle part again, it's back at a constant negative velocity, and we repeat this over and over again. So how do we tell the difference between A and D? Well, we have to look at the angles of the ramps. We don't need to do any real trig, but we know the steeper the angle of the ramp, the more force is going to be along the ramp, or the faster it's going to roll. I mean, that's kind of intuitive, right? If you roll a ball up a ramp, the steeper the ramp is, the quicker it'll come back. But if we were going to break this down in terms of forces and angles and everything like that, what we'd really see is that that component of gravity that's along the surface will be greater if the ramp is steeper. The two extremes maybe are helpful to look at. If the ramp was completely straight up, then all of gravity will be along the ramp and straight down. So then, we'd have the maximum acceleration due to gravity, whereas if the ramp was flat, then all of gravity is perpendicular to the ramp, like it is in the middle, and you get no net force or acceleration. So we want a higher magnitude of acceleration where the ramp is steeper, which is on the left. And what does a higher magnitude of acceleration mean? It means a steeper slope on our velocity graph. So A has the steeper slope on the left and the shallower slope on the right. So A is the answer. So this question has a whole lot of concepts in it, but I think it really does drive home the thing that you were asking about before, which is that the relationship between the signs of velocity and acceleration tell us about whether the object is speeding up or slowing down, and that the acceleration itself tells you nothing about the direction of the object's motion. Right here, my acceleration, this first hump on the acceleration chart, it's all positive and it's some constant value. That only tells me about the slope of that corresponding line on the velocity graph. That you can see that velocity, that's where that line is sloping upward in A, contains both negative and positive velocity, right? So it's moving both backwards and forwards at different times during that interval, even though we had this constant positive acceleration. The reason being, at first, when the ball first hits the ramp, we have a negative velocity, right? It's below zero, but a positive acceleration. So since the signs are opposite each other, the object is slowing down, the velocity is coming towards zero. But then, once it crosses through zero, we have a positive velocity and a positive acceleration, and so the object is speeding up, coming away from zero in the positive direction. So yeah, this example kind of reinforces that. I'll leave an exercise for you if you want. We're not going to go over it now, but if you want to try plotting out the position versus time of the ball along that axis, that would be a good, maybe a little bit difficult exercise. But just a rough plot of that, I think, would be a good exercise. Okay, so now let's do one final clicker question for the day. We have two asteroids that are moving together and collide. We know nothing about the final state other than momentum is conserved and there's no external forces are present. So we're given their masses and initial velocities. We got 2m moving to the left, and 2m moving to the right, and m moving to the left, and the m is moving twice as fast as the 2m. So there's our setup, and we're given a bunch of scenarios, and you just need to decide which of these is true. And this one's kind of tricky. Give you another minute or so. I'm asking this as I'm about to close the voting on like the very last clicker question of the whole course, but do you think that it would be helpful if I gave like even more time for you to work on these, or is it good for me to just give you a couple minutes to work and then kind of go over it, knowing the latter is good, if this is the way I'm doing it is okay? Okay, well I guess that's good. If the answer was opposite that, I guess, sorry. Okay, so that being said, let's go over this one together. Okay, so the answer is C. Let's find out why. So this is a collision problem that we're used to analyzing it in terms of momentum and collisions. Like that's how we've always done it. But now let's take a look at it from a perspective of kinematics and forces and acceleration. And maybe before we start working through the choices, let's figure out what we know, or like try to describe the situation in terms of this new way of thinking about it. So we're told no external forces are present, which means that the only forces here are F on 2 by 1 and F on 1 by 2, right? Forces on each object by the other. And we know due to Newton's third law that those are equal and opposite, right? They have to be. Whatever force 1 does on 2, 2 has to do on 1. And we'll talk about this in terms of impulse in a second. But just given that, we also now can use Newton's second law that force on 1 by 2 is going to result in an acceleration given by like m1 times a1. And same for 2, that this force is equal to m2 times a2. And we'll just put them in terms of magnitude. We know they're equal and opposite, that one acceleration is going to be positive, one's negative, but if we take the magnitudes, then we're all set. So m1a1 equals m2a2 is really just saying Newton's third law, that f1 on 2 is equal to f2 on 1 in magnitude. Now, once we have this, we know that m1 is greater than m2, right? m1 is twice m2. And if that's true, and these two things are equal, then a1 has to be smaller than a2, right? In order for this equality to hold, if m1 is bigger, then a1 has to be smaller, which is exactly what C says. The slower asteroid, which is m1, has a smaller magnitude of acceleration. And so that is true. Let's walk through the other answers and see why they're not. Well, A, the two asteroids experience equal and opposite accelerations. We just decided that that's impossible, right? We said because if the m's are not equal, then the a's cannot be either in order for that equality to hold. So that one's just kind of misguided, right? That's kind of going on this, oh, it kind of sounds right. But no, the forces are equal and opposite, not the accelerations. Okay? B, both have zero acceleration since there is no net force. Again, kind of grasping at some ideas here, but it's putting them together in an incorrect way. Correct, there is no net force, but the net force refers to the net force on the system as a whole. So yeah, if we draw a box around object 1 and object 2, then there is no net force on there, and there's no total force that's moving the center of mass of the system, really is what that would mean. And that's true, but there can be however many forces acting within it, right, as long as they cancel out. They're equal and opposite. So there is no net force. That's true, but that does not mean that both objects have to have zero acceleration. Yeah?
Like, if you were to place B, would you say that, like, the total system, or, like, the net acceleration is zero, essentially?
Yeah, but I get what you're saying, and there's something truthful in it, but net acceleration is not a useful value. Like, it's not conserved, right? If we add a1 to a2, we get some non-zero value, even though we started with neither object accelerating. So acceleration is not something that we would ever calculate a net for, but we would calculate a net impulse or change in momentum. So it's related, but yeah. Net acceleration isn't something that we do. So if you're ever adding two accelerations of different objects, you're probably doing something wrong. C, we've already discussed it's right, and D is just the opposite of C. D is saying that object 2 will have a smaller magnitude of acceleration, which is just backwards based on the masses. And then E, it's true we don't know whether this collision is elastic or inelastic, but we don't need to know that to answer this question. But that does hit on a key point, that this collision could have a variety of different ending states, right? Let's see what the initial momentum is. We have object 1, 2mv, positive, right? Just 2m times v, and it's moving to the right. And then object 2 is 2mv also. It has a higher velocity and a lower mass, but it still has the same magnitude of momentum pointing in the opposite direction. So our total momentum in this system is 0. That's what we want to add together. So 0 total momentum, which means we have to end up with 0 total momentum as well. But that could be completely inelastic. If they stuck together, That would just mean they stick together and stop, right? Zero velocity times whatever mass gives me zero total momentum. They could bounce off each other, right, and move in the other direction, which is also fine. It's just they have to have equal and opposite momentum. There could be a y component introduced. It really doesn't matter as long, and they could break apart as long as the total momentum is zero. And we'll find, well, assuming they don't break apart, then this doesn't really make sense, but we'll still find that C is going to be true regardless of which of those situations occurs. Let's pivot to thinking about this in terms of momentum to see why that's true. So we know that delta P is equal to F net times delta T, right? And that's true for each individual object in the system as a whole. But if we decide that the F net is equal for both of the objects, and this is the F on each individual object, so now we're not talking about net force on the whole system, we're talking about net force on each object. But if the force on each object is equal and opposite, the delta T is the same, right? Because the delta T is the amount of time that they're in contact, which is inherently has to be equal for both objects, right? The amount of time one is in contact with two is equal to the amount of time two is in contact with one. And so if the forces are equal, then the delta P's are going to be equal and opposite as well. So the change in momentum for each is equal and opposite. And so let's pick an example of one of these. So let's say the completely inelastic case, which we know is valid, where they collide and stick together and stop in the middle. In that case, object 1 comes from having a velocity of v to having a velocity of 0, right? So its magnitude of change in velocity is v, or its magnitude, and its change in acceleration is v over delta t, whatever that is. Object 2 goes from having a velocity of 2v down to 0. So its magnitude of acceleration is 2v, or negative 2v, but the magnitude is 2v over delta t. So just from that, we can see that if they come to a stop in the middle, object 1 will have to slow down less than object 2 because it was moving slower to begin with. And so that also proves C, that the slower asteroid has the smaller magnitude of acceleration. And I won't do the whole thing out, but you can also just pick any final state of this that obeys conservation of momentum, but like any situation where they bounce off each other and go the other way, object 1 is going to be moving slower than object 2 because it's heavier, right? So if their momenta are going to be canceling each other, object 1, which is more massive, needs to have a smaller final speed. And so no matter what, object 1 is going from a smaller initial speed to a smaller final speed. And so it has this small change. Whereas object 2 is always, no matter what, going from a larger initial speed to a larger final speed than object 1. And so, yeah, again, I'm not going to work out the proof on the board, but if you do, you'll see that there's no final situation that occurs that does not obey option C, regardless of the elasticity of the collision. So we can do this next one. It's kind of weird because we changed the velocity, but this is just a closer to connect a collision problem with momenta with our force method of looking at things. This is a very similar situation, except now they're both moving at the same speed initially. Still, object 1 is 2m, object 2 is m, but now they're moving together with equal and opposite speeds. And then when they collide, the final state is that object 1 stops and object 2 is moving the opposite direction at speed v, which we'd have to figure out. But if we fill in this momentum chart, I won't spend too much time here, but we know that the momentum of object 1 is going to be twice the magnitude of object 2 because it has the same speed but twice the mass. And so our total momentum will be some amount of momentum to the right? So there's our initial state, no external force, and so the final total momentum is the same as the initial. And since we're told that the final momentum of object 1 is 0, then that means the final momentum of object 2 has to be 1, which is how we figured out that it's moving the opposite direction at speed v. So then there's two ways we could fill out this delta p thing, but either way, object 1 goes from having a momentum of 2 to 0, so its change must be negative 2. And of course, that means the change in momentum of object 2 has to be 2. Whether we say that negative 2 plus 2 equals 0 or negative 1 plus 2 equals 1, it's true both ways. So this is our very simple collision problem where we work it out in terms of a momentum chart. And what we find here are these equal and opposite momentum changes in the objects. And so let's take those and then try to work out the kinematics of this system. So relating just the forces here, again, we have Newton's third law turning into Newton's second law, but we find that in this case, the acceleration of object 1 is 1/2 that of object 2. Or in other words, the acceleration of object 2 is twice that of object 1 in the opposite direction. Like we said, object 2, since it's lighter, has to have a larger acceleration. And so if we turn these into the acceleration graphs, this middle dotted line region in between the two dotted lines is while the collision is occurring, and then so to the left of it is before, and to the right is after. Asteroid 1 on the left, asteroid 2 on the right. So for both of them, the acceleration before and after the collision is 0, right? There's no forces at all when they're not in contact. But during the collision, both of the objects experience some force that is equal and opposite, which results in these accelerations. So object 1 has some negative acceleration that stops it, right? It was moving to the right and comes to 0, so it has this negative acceleration. And object 2 was moving to the left and now is moving to the right. It has this positive acceleration that has twice the magnitude of that of object 1. So great, here's our acceleration graphs that show what's happening during the collision, where we have two objects moving without accelerating, and then they contact, have equal and opposite forces, which do not produce equal and opposite accelerations. Now let's quickly turn those into velocities. For object 1, like we said, we go from moving forward to 0 at a constant negative acceleration of -1. So we have a downward sloping velocity during that interval. And for object 2, we have the opposite, upward sloping, except this one goes all the way through 0 and up to a velocity that's in the opposite direction. And then position, this one's a little funky, but object 1 before the dotted line has a constant positive velocity, so just a straight line. Then during the collision, it has a positive velocity, but that's decreasing. So the position is increasing, but at a slower and slower rate. So that's why you get this curve that becomes more and more shallow, and then it's stopped. So then we have a constant 0 position with 0 slope. And for asteroid 2, I'll let you figure that one out yourself, but it shouldn't be too bad given the other ones. So this one, even though the answers are already here, I really think this is a great example to just stare at and kind of make sure you understand what each of these graphs is representing. Because if you do, I think you're in good shape for the final, and you could just work on the quantitative part. So I said in Canvas, but my review session will be this Friday in this room from 4:10 to 6:30, and I'll be doing lecture style, but of course, welcoming questions. Yeah. Capacitors, you weren't quizzed on non-zero angular momentum, so like stuff like carousel problems or stuff where there is angular momentum, that, and then kinematics. Oh yes, you'll see exponentials but with capacitors. You won't have to do like the fluid ones where there's like H, but yeah, capacitors are inherently exponential.